We're now going to start talking about immunity. The immune response is the body's way of dealing with invaders. Most organisms have ways basically to ward off unwanted pathogens. Bacteria have restriction enzymes, which they use to chop up the DNA of invading viruses. So when the bacteriophage tries to inject its DNA into the virus, these restriction enzymes will kind of chop up the DNA when it's injected into the cell so that the DNA can't be read. So this is the bacteria's way of kind of fending off viruses. If we think about other organisms such as worms and insects, they have cells that move freely through their bodies that are on defense, ready to attack pathogens. The further that we climb up the evolutionary tree, the more sophisticated the immune system becomes. Vertebrates have developed immune memory. Their cells are able to remember a foe. So the defenses that we have available to us today within our bodies basically have a very long evolutionary history, kind of reaching back millions of years. And it's a system that has been refined and added to over time. It's been refined throughout the life of eukaryotic cells. So our immune responses, we can basically classify them as being either innate or adaptive. So innate immunity is basically an old method. So this was kind of the method that first evolved. It's an old method of protection. It existed in one form or another in all eukaryotic organisms. And it's just a generalized set of responses that don't really vary based upon the pathogen that's being confronted. Because of this, innate immunity is sometimes called non-specific, because it doesn't matter which pathogen the organism is fighting, the immune response is going to be the same. Whereas adaptive immunity is newer, and this occurs in all vertebrate animals. Remember, we said that they can remember their foe. Their cells can remember an old foe that they have fought. So this type of defense matures over time, and it's very specific to the pathogen that's encountered. And this is why adaptive immunity is also called specific immunity or acquired immunity, because it's specific to the pathogen and it's something that you acquire during your lifetime. Once you've kind of come up against these different pathogens, you remember them. Adaptive immunity, though, requires a 4 to 7 day window to become fully activated. So it's a much slower process when it comes to fighting an infection as compared to innate immunity, which is a much more immediate response. But being able to recognize a pathogen that has been previously fought can allow your body to more aggressively defend itself when exposed to that pathogen. So immunity can be kind of divided into 3 lines of, so we kind of think of them as 3 different lines of defense that we have. And the first and the second line of defense fall under our innate immunity, while the third and final line of defense is our adaptive immunity. Right now, we're just going to focus on the first and the second line of defense, which comprise our innate immunity. So here in this chart, you can kind of see once again, it's talking about the host defenses. We've got innate on the left and adaptive on the right. We said adaptive is our third line of defense, and we're not going to spend time talking about that right now. We want to focus on our first and our second line of defense that fall under our innate response. So first off, we'll talk about this first line of defense, And coming down off of that, you can see physical barriers, microbiota barriers, and chemical is what we're going to talk about first. So our first line of defense, and we mentioned that we've got these physical barriers, all right? So if you want to think about it, if a pathogen is trying to gain entry into your body, your first line of defense is up, right? So this first line is basically going to prevent the pathogen from entering your body. So basically, we're looking at your skin. So your skin is a physical barrier that prevents microbes from entering your body. The skin obviously is made up of epidermal cells. It consists of many layers of continuous sheets of these tightly packed epithelial cells. There's hardly no room in between them at all. They're just packed one on top of another and stick closely together. So the skin is pretty impervious. It's waterproof. Our palms and the soles of our feet have much thicker layers of skin that make it really tough for anything to cross those areas of our bodies. So basically, our top layer of skin is dead. There's probably about 50 layers of dead cells, and we shed them periodically. Now, if you think about it, that really helps to remove microbes from the surface. So this is what we call sloughing. So it's estimated, I don't know who does these types of counts, but it's estimated that you lose some 40,000 skin cells every second. So we're constantly losing cells, and this makes it very hard for microbes to gain a foothold on the surface, especially if that surface is constantly shifting. So anything that tries to take a seat on one of your skin cells is going to be removed when the skin or when the cell is shed from the body. We also tend to sweat the surface of our skin. So sweating can also remove microbes. So right now we're simply talking about kind of the flushing action of physically removing microbes from the surface of our skin because of the sweat kind of dripping off your body. So adding that liquid to the surface and having it kind of remove the microbes. We'll talk about the chemical properties of that in a moment. Now we also have mucous membranes that are part of our physical barriers. So mucous membranes basically line all the body entrances. So our lungs, our bladder, and these are specialized tissues that make mucus. So mucus is very sticky, it's very viscous, and it's great at trapping these pathogens into the body so that they can't get past the boundary. So we've got the sticky mucus that helps to trap our pathogens. Now there's also, pathogens can also be flushed from the body. So we have ears that come from our eyes, obviously, that wash debris, right? We've all gotten something in our eye and our eye starts to well up with tears, and so it's helping to kind of flush out that debris. But the same thing works with pathogens. So it helps to remove pathogens from the eye. Urine also helps to flush microbes out of the body. So that's also another flushing action. Even the constant kind of rinsing of saliva, the production of saliva in our mouth and the swallowing of it helps to limit the microbes that can adhere to the tissues in our mouth. We can also think about, even though we may not want to think about it, but defecation, vomiting, diarrhea, they all expel microbes. So a lot of times this is in response to the toxins that microbes might be producing, and the muscles of your gastrointestinal tract may contract so vigorously, and that results in you vomiting or in diarrhea coming out the other end, and all that helps to get rid of microbes from your body, okay? Now, one system that is lined with mucous membranes is our respiratory system. Air and potential pathogens are taken in through the nose, and the mucus and hairs within your nose help to trap particles, pathogens that might be hitching a ride on them. And then within the airways, the mucus assists what's called the mucociliary escalator. So the mucus is basically swept away from the lungs and towards the mouth by these ciliated cells of the trachea and the bronchi. So the mucus traps the pathogens, and then the cilia helps to move all that back up the trachea. Coughing, where you can cough up this mucus, or sneezing out the mucus, all that helps to remove microbes as well. Then in the urinary tract, we have the cleansing of the urethra by the flow of urine. This is another physical factor that helps prevent microbial colonization. There's also vaginal secretions. Likewise, they help to move microorganisms out of the female body. Now we have the microbiota barrier. So this is also part of our first line of defense. We've already mentioned a lot about the microbiome. We know that it can create an unfavorable environment for pathogens. So our resident microbes and pathogens tend to compete for limited nutrients. So our resident biota usually try to shift the game in their favor by altering the pH in basically an act of microbial antagonism. And in the short video that you watched of the invisible universe of the human microbiome, you saw the immune system depicted as a creature that our microbiota basically trains. So our immune system learns to leave it alone, because we don't want our immune system attacking our own microbiome, but we do want it to recognize potential pathogens and help us get rid of those. Then the last part of our first line of defense are chemical barriers. There are such things that are called lysozymes. These are antimicrobial enzymes capable of breaking down cell walls of gram-positive bacteria because they help to break the bonds in the peptidoglycan, which causes cell death. Lysozymes are found in tears, saliva, nasal secretion. They're even in urine. We've got other areas of the body where we show low pH. So earwax, saliva, vaginal secretions, they all create low pH environments, which is something a lot of microbes do not like. And then we've got these other chemical barriers. Semen, so the seminal fluid basically provides antimicrobial protection for the sperm, especially while it's in the female reproductive tract. Lysozymes are a component of that fluid. We have sebum. So basically, this comes from your sebaceous glands of the skin. They produce this oily substance that's called sebum, that prevents hair from drying and become brittle. So the sebum forms a protective layer over the surface of the skin, and one of the components of sebum is unsaturated fatty acids. And so that can actually inhibit the growth of certain bacteria and fungi because the low pH, it basically creates a low pH environment, pH between like 3 and 5, and because of the fatty acids that are being secreted. So it creates what we call an acid mantle, and the acid discourages the growth of many of the microbes. And when it's warm, we tend to sweat. And so that helps to cool us, but also transports a lot of salt to the surface of our skin. So this makes our skin a pretty salty place. So our skin is constantly shifting ground due to the sloughing of cells. The outer layer is dry, salty, and acidic. So it's really not your typical Holiday Inn for bacteria.